Begin with a point on a straight path in an input plane. Send that path through one mysterious function. One direction becomes a ray racing outward. A perpendicular direction becomes a circle that never grows. Tilt the path between them, and the output spirals, rotating as its radius changes. 3 motions, 1 rule. What can read direction in one plane and turn it into growth plus rotation in another? The previous film ended with an inverse question. If an exponential lands at a complex number, which input produced it? First, understand the forward machine. Call its input w and its output z, with z equals e to the w. Exponentials turn addition in the input into multiplication in the output. E to the u plus v equals e to the u times e to the v. That familiar rule separates growth from rotation. Give the input rectangular coordinates, w equals x plus iy. Here x is horizontal and y is vertical. Split the sum inside the exponent, one operation at a time. First write e to the x plus iy. Then use the addition rule to obtain e to the x times e to the iy. The two input directions now control separate visible factors. Euler's formula identifies the second factor, e to the iy equals cosine y plus I sine y. Substitute it while e to the x stays fixed. Now z equals e to the x times open parenthesis cosine y plus I sine y, close parenthesis. The bracket is a unit arrow at angle y. The positive factor e to the x scales it. So the real input x becomes log radius, while imaginary input y becomes angle. Hold y fixed and slide x. The output z follows one ray. Increasing x enlarges its radius, while decreasing x draws it inward without reaching 0. Reset x to 0 and slide y. The radius stays 1 while the arrow rotates. Move x and y together along a slanted line. Scaling and turning happen together, so the output traces the opening spiral. Test 1 exact input. W equals natural log of 2 plus I times pi over 3. Read the horizontal coordinate first. Exponentiating it gives radius 2. Read the vertical coordinate next. The angle is pi over 3. Therefore z equals 2 times cosine pi over 3 plus I times sine pi over 3. Project the arrow. The components become 1 and square root of 3. The output is 1 plus I times square root of 3. Transform the whole grid. Draw a rectangular grid in the W plane, with x horizontal and y vertical. Follow a vertical line, x equals c. Its x stays fixed, so every output has radius e to the c. As y changes, the line wraps around a circle. Now follow a horizontal line y equals c. Its angle stays fixed, so varying x sweeps along a ray. Each grid cell bends into a polar sector while the plane wraps. The transformed grid reveals a hidden repetition. Raise the input w by 2 pi I. Its x-coordinate is unchanged, while y gains one complete turn. The output arrow returns to exactly the same point. Algebra agrees. E to the w plus 2 pi I equals e to the w times e to the 2 pi I, which equals e to the w. Repeat any integer k of turns, and e to the w plus 2 pi ik still equals e to the w. Shade one horizontal strip of the W plane from 0 to 2 pi. Watch that strip wrap once around every non-zero point of the z-plane. Lift to the next strip, and it covers the same output. Lower to the strip below, and it repeats. The exponential remembers horizontal position as radius, but it forgets how many complete vertical turns occurred. That lost count is why its inverse cannot return one input. Now, reverse the machine for a non-zero target z. Write z with radius rho and angle theta. To solve e to the w equals z, let w equal x plus iy, and compare the controls. Matching radii gives e to the x equals rho. So x equals natural log of rho. Matching direction gives y equals theta plus 2 pi k. Therefore, every solution is w equals natural log of rho plus I times theta plus 2 pi k, where k is any integer. Apply the full answer to our earlier output. Z equals 1 plus I square root of 3. Its radius is 2, and one angle is pi over 3. So, all inputs are the natural log of 2 plus I times pi over 3 plus 2 pi k for every integer k. Plot several as vertically separated points. All map to the same z. 0 is different.
Since e to the x is positive for every finite x,
Every output has positive radius. No finite complex input maps to 0, so 0 has no complex logarithm. The exponential has another remarkable property. Its local change copies its value. Give w a small increment h. The output change is e to the w plus h minus e to the w. Factor out the stationary e to the w. Dividing by h leaves e to the w times e to the h minus 1 over h. As h shrinks to 0, that second factor approaches 1. The derivative of e to the w is therefore e to the w itself. Reconnect that equation to the arrow. At each input w, the derivative is the output z itself. Its magnitude tells how strongly a tiny step is scaled, and its angle tells how the step turns. Move to larger x, and both the arrow and local response grow. Move upward in y, and both rotate. The formula says the exponential carries a scaled, rotated copy of its own motion at every point. Turn the map into motion. Start from z0 with radius r0 and phase phi. Then define z of t equals z0 times e to the open parenthesis alpha plus I omega close parenthesis times t. Split the exponent. The result is r0 times e to the alpha t times e to the I open parenthesis omega t plus phi close parenthesis. Alpha controls growth or decay of the radius. Omega controls angular speed. Differentiate once, and the velocity is alpha plus I times omega times z. Separate the velocity into two arrows. The alpha z component points along z, outward for positive alpha, and inward for negative alpha. The I omega z component is perpendicular, producing rotation. Add them and the tip follows their combined direction. Turn alpha below 0, the orbit spirals inward. Set alpha to 0, only rotation remains, tracing a circle. Turn alpha above 0. The orbit spirals outward. One dial changes decay into rotation and then growth without changing the rule. Now, let the moving arrow draw a signal. Place time along a graph beside the complex plane. A guideline stays attached to the arrow's real projection and the newest waveform point, so their values cannot drift apart. As the arrow rotates, that point writes r0 e to the alpha t times cosine of omega t plus phi. With alpha 0, the envelope is constant. Negative alpha damps the wave. Positive alpha amplifies it. The spiral and the graph are one motion viewed two ways. Quantum mechanics uses a particularly important setting of this machine. For a component with definite energy E, its time factor is e to the negative I et over h bar. Equivalently, psi of t equals psi of 0 times e to the negative I omega t, where omega equals e over h bar. The exponent is purely imaginary, so alpha is 0. The amplitude rotates without changing size, and its squared magnitude stays fixed. This is phase evolution, not probability growing with time. A single overall phase rotation does not change observable probabilities by itself. The payoff appears with two energy components. Give them energies E1 and E2. Their angular speeds are E1 over h bar and E2 over h bar. so the angle between them changes at the difference. Add the arrows first. At some times they reinforce. Later, they partly cancel. Changing relative phase can produce changing interference, even though each component keeps its magnitude. Slow the picture so the two phase arrows merely rotate together. Their small speed difference makes the resultant swell and fade slowly, like beats from nearby musical frequencies. We are not deriving a quantum experiment yet. We are isolating the bookkeeping that makes superposition intelligible. Complex exponentials store magnitude and phase. Time advances phase, and phase differences control how alternatives combine. Return to the two planes and follow through the story. The input w equals x plus iy becomes the output z equals e to the w. Horizontal input x becomes log radius through e to the x. Vertical input y becomes angle through e to the iy. A slanted path becomes a spiral. Addition becomes multiplication. Full turns create repeated inputs, giving the complex logarithm. A purely imaginary time exponent becomes quantum phase rotation. The complex exponential is where growth and rotation become one idea.